So integration, this is the process we're going to talk about. Now, integration is defined in any modern textbook you look at as reversing the process of differentiation. I don't think historically that's how it was devised. It was devised as solving separate problems. Don't forget, differentiation solves problems to do with rates of change with respect to time or some angle or whatever, whereas integration, if you go back to our original discussion about the calculus, actually finds areas under curves, and that's what we'll be doing later on. So they're actually defined and devised for different problems, but they are related topics. Okay, so any modern textbook will present it in that fashion, that we're reversing the differentiation process. Okay, and sometimes that's termed solving differential equations as well in some textbooks. Alright, so that's how I'm starting off this presentation. We're going to say that integral calculus or integration reverses the process of differential calculus, or what's called differentiation. So what you've done so far with me in previous lectures is given an equation, something like y is equal to x cubed plus 3. We've differentiated that using standard differential tables. This is all work we've covered before in previous lectures. So we go from the format of ax to the n, which is the x cubed upon 3 here, if I perhaps write this over here. So we start off with a function, something like y is equal to, in this case it's the x cubed upon 3, and we can, if we want to, we can write that as y is equal to 1 upon 3 multiplied by the x cubed. Okay, so there's our sort of ax to the n format. This is the a, this is the x, this is the n. So we start with the y is equal to ax to the n format shown in the table here, and then we differentiate it following the patterns through anx to the n minus 1. So in the above case we would end up with differentiate, don't forget it's dy by dx for differentiating, so dy by dx would equal to be 3 upon 3 x to take 1 off the index x to the 2, and that gives us the value of x squared. So our first differential, the dy by dx in this case, is x squared, and that's what's shown in the explanation on the right hand side. Okay, that's differentiation, and that's what we've been doing. What we're going to do now with this work is to start from the dy by dx equation, and we're going to get back to the y equation. So the whole essence of this now is starting with a differential and then try and get back to the original function. We're reversing this process, in other words. So just as there is a standard differential table, there's also a standard integral table, and do be careful when you're doing calculations or you're doing work on the integration, differentiation, you pick up the correct table, because in the formula sheets you'll find there are two tables. So on the previous slide we have the standard differential tables. Now we're looking at the general solutions for integrals, and this is a standard integral table. Okay, I'm just showing you one form at the moment, but there obviously are tables larger than I'm showing here. Okay, so these standard integral tables are available to specify what's called general solutions, and you'll see what I mean by that a bit later on, to what's called standard integrand. If you want a bit of jargon here, the ax to the n in an integral format is actually called the integrand. It's a bit of a jargon term for you. And if we integrate the integrand, we end up with a solution for the integral, and this is a standard form here for the integration of ax to the n. It's ax to the n plus 1 divided by n plus 1. And notice it also has a plus c. Okay, now be very careful. You must add the plus c when you're integrating. For when you're finding general solutions, which we'll be looking at first of all, you must add the plus c as it says in that table. I'll show you why in a few slides time. Okay, so that's very important for the moment. You add that plus c. And this expression, this integrand, works for any values of n except when n is equal to -1. If n is equal to -1, of course you're dividing by 0, and you can't do that in mathematics. So it doesn't work when n is equal to -1. There's another solution we can use, which we'll see a bit later on. You'll also see in the integration process that we use a particular symbol. Integration is denoted by this elongated s. It goes back to the old English, I think, the sort of way they used to write S's in back in centuries ago, and that means summate, sum up, add up. Okay, so you'll often see in these kind of problems this integral symbol here, so it's very important you recognise that. So just like, for example, if I was to give you something like the square root of 9, you would know what to do with that. You know what the square root of 9, you know how to deal with that. What we're going to see today are things like the integral of 3x squared with respect to x, and again this integral sign is trying to tell you what to do with that function. Just as the square root is trying to tell you what to do with the 9, the integral is trying to tell you what to do with the 3x squared here. So that's the sort of formats you're going to see in all the questions we go through. The functions will obviously be different and the variables be different, but that's the format we're going to see. Okay, so what we're given here in this particular example is a little example of how to solve a differential. So we're starting off here with a dy by dx equation. That's a differential, don't forget. We must use that notation when we've differentiated dy by dx, and it's equal to, in this case, the x squared. What we've got to do now is integrate this, or in other words, solve the differential, another way of saying the same thing. So we need to be able to go through this standard process of integration. So the first thing we would do, given equation 1, is to rearrange it. Notice what I've done on the next line is I've just multiplied both sides by the dx. I've got dy by dx on the left hand side equals to x squared, so multiplying both sides by dx in this case, I would get dy is equal to x squared, and that's multiplied by the dx. Okay, once I'm in that format with the y terms on the left hand side and the x terms on the right hand side, I can integrate, I can solve this problem. And that's what I'm doing on the next line. See, the integral symbol is been used here, so I'm integrating. I put 1 dy, I put the 1 in there because sometimes it helps students understand what's going on. So integrate 1 with respect to y, that's the way we term that. And on the right hand side, I'm integrating x squared with respect to x. That's how we read that, okay? And the reason I put the 1 on the left hand side is when you integrate the 1 with respect to y, you get y. I'll just take you through that once. I'm only going to do this once just to show you. We'll just accept it thereafter. So just over here, what I'm saying is here, I'm integrating 1, if I put against it y to the naught with respect to y, that's what I'm kind of saying there. Don't forget y to the 0 there is 1, so I've still got 1 effectively here, 1 dy. I can put a 1 there if I want to, 1 dy. And when I integrate it following the pattern, you can see I've got the ax to the n pattern here, ax to the n, where a in this case is 1, the x is y, and the n is 0. And following the pattern through above, in the table, this little table at the top, standard integrals, I would end up with 1 y to the 0 plus 1 over 0 plus 1. And if you do the numbers on that, you'll find you'll get y. Okay, because 1 times y to the 1 is y divided by 1 is y. Okay, now don't worry if you don't follow that, I'm not bothered. You just accept that when you integrate 1 with respect to y, you get y. Okay, but that's where it comes from, this standard form that we're using in our standard integral tables. On the other side of the equation, I'm integrating the x squared. So over here, if I put it over to this side here, I've got the integral of 1 x squared with respect to x. So you can clearly see I've got my ax to the n format. A is 1, the x is x in this case, and the n is 2. So again, following the above pattern through, when I integrate it, I will get the x to the add 1 to the index, 3 over the n plus 1 over 3. And then I add my c at the end. I should add a c at the end. Okay. So that's what I'm doing. That's what we're going to do in a moment. We're going to do this integration process, and that's called solving a differential equation. But notice the process there. We first have to multiply both sides by dx to get all the y terms onto one side, all the x terms onto the other. Then I integrate both sides. Again, what you do to one side, you do to the other. So if you're going to take an integral of one side, you have an integral of the other side, so not affecting the equation here. And I end up with my solution. So this is the solution here to this particular question. Y is equal to the x cubed upon 3 plus c in this particular case. Okay, let's have a little go at just practicing that expression. Okay, and so let's have a go with these questions here. So we're going to start off with integrating these terms. Let's go try and do them down here below. Okay, so question 1. We're asked to integrate x to the 4 with respect to x. So integrate x to the 4 with respect to x. That's how we read that. If you want to think of that as a 1 in front of the x, then do. It's 1x to the 4, and that's my ax to the n pattern. So right underneath this, the ax to the n, then you've got the standard pattern. So we're using this standard form. I put it at the top of the screen for convenience, the ax to the n. And when you integrate it, what do you get? If I do it over here, when I integrate 1x to the 4, following the pattern through, I will get 1x to the n plus 1, so that's 4 plus 1, so that's to the 5, over n plus 1, so that's 4 plus 1, that's over 5. And I should add my c. I haven't put the c in the above expression because I actually talk about it later in the presentation, but we should really put the c at the end of each of the expressions here. Okay, so all I'm doing is following that pattern through the ax to the n format in my integral table above there. If I take the next one, item 2 here in my list above, I'm now integrating 5x with respect to x, so we integrate 5x with respect to x. Okay, and again, if I think of my ax to the n format here, this is ax to the n. What's the value of n in this case? Well, we don't write it, but the value of n is a 1 there. There's a 1 against the x, so I've got my 5x to the 1. And if I follow the integration process through, following the pattern, I will now get 5x to the n plus 1, so 1 plus 1 is 2, over n plus 1, so that will be over 2. And again, I should put my plus c against that. Okay, so this is the sort of pattern that we're following through in each of the questions. I'm going to try and go through as many as I can here. We'll get lots of practice at this because we're going to concentrate on the polynomial first of all, before we look at things like sines, coses and tans, integration process later on. 3, the integral of x with respect to x. So again, if you want to think of it, we've got a 1 in front of the x there, if it helps you to put these in, and there's 1 as a power there. That's my ax to the n, and that equals to x to the 2 over 2, and add my c. Solutions are shown above in the brackets, just add the c in the brackets. Okay, I'm just going to work through these on the board here, a few of these on the board. You carry on if you think you can, please feel free to carry on. Okay, and item 6, I just messed about with indices at the end. There's nothing wrong with this solution here, the negative x, negative 1, but don't forget from our laws of indices, our rules of indices, we can use the negative index here to rewrite that. So that's what I've done here. I've just rewritten it using this rule of indices. And the one probably that's most difficult to deal with is item 7. Let's have a quick look at that, because that's also to do with indices. So item 7, this is something we've mentioned many times now, I don't know if you remember, but if you've got the square root of a function, square root of a variable, square root of a constant, whatever, we can actually write that as the integral in this case of x to the power of a half. Don't forget that, that's really useful to remember. So that's going into fractional indices using the rule here. Okay, so that's what we've done to take it from here to here. Okay, so be aware of that, that's indices. And don't forget, that's just putting it into what's called a standard form. That's not integrating. Some students think they've integrated when they've done that, but they haven't. No, you haven't integrated. You've just made it into standard form, and now it's of the form ax to the n, so you can now integrate it. So I've got to integrate it, so that's going to be x. So if you stick to the fractions, that will be 3 upon 2 divided by 3 upon 2 plus my c. That's where it gets a little bit confusing now, because we're dealing with fractions. Now that dividing by 3 upon 2 is like multiplying by 2 upon 3, so I could write that now as this. Okay, so you could really play with it from there if you wanted to. I'll just show you this, don't worry if this confuses you. You could have 2 upon 3, I'm sort of playing with my indices. Because I've got the half in the index, that's a square root, so I could actually write it as the square root of x cubed. Okay, but that's an icing on the cake, that last line there. So what you're looking at there is the basic integration process. We're going to use that in most of the questions we're going to look at. That's the process we're going to go through using the standard table at the top of the page there for the integrand ax to the n. Okay. Example 4 shows you the x plus x squared to be integrated. What I'm trying to show here is that you can integrate the x on its own. You can integrate then the positive x squared on its own. They're both of the form ax to the n. As long as they're separated by a positive or a negative term, then we can integrate them individually. Okay, so just to sort of reinforce that, if I'm given the integral of x plus x squared, and notice they're in a bracket. That's very important, having that bracket around them. Make sure you keep a bracket around them. Then I can just integrate them individually. So that will be the integral of x squared, that's x to the 1, of course. That becomes x to the 2 upon 2, so I integrate that term, and then I look at the next one, integrate the 1x squared, so that's going to be plus the x to the 3 upon 3, and then add my c to the next term. All right, so each term there on the left hand side integrated separately. That's all that's showing there. And the same here, exactly the same thing here, just integrating the terms separately. If I'm integrating, in this case, 3x to the 4 minus 5, and if you want to think of that as x to the 0, if that helps you, you can do, with respect to x. Then again, each term can be dealt with separately. So that would be here the 3x to the 4, that's ax to the n, that becomes 3x to the 5 over 5, so that term's dealt with. A negative 5x and 0 is still the negative 5, which I've got there. But following the pattern through, that will be negative 5x to the 0 plus 1, so that's x to the 1 over 1. Okay, if I put the 1's in, there's a 1 there and a 1 there, plus my c. So that's where they get the final solution from, of 3x to the 5 over 5 minus, in this case, the 5x and plus the c. Let's have a go at a few more questions like that. That's the only thing that's different here. We've got multiple terms now in the integral. But let's have a little play with this for a few minutes and see how we get on with these questions. So question 1 above, we're asked to integrate, got several terms there. We've got the x cubed plus the x squared minus an x, and then plus a 2. We're integrating with respect to x. And again, it's very important you keep that format in your solutions. So each of those terms there are ax to the n. This is an ax to the n. This is an ax to the n. They're all of the form ax to the n, and this is ax to the n if I write x to the 0 against it. All right, all of the form x n, all separated by a plus or a minus, so we can just integrate them individually. Integrating, we'll get x to the 4 upon 4, following my standard integrand in my table. That's the first term integrated. Integrating the second term, we will get x to the 3 upon 3. Integrating the third term, don't forget that's the negative 1 x to the 1 there, if that helps there. So integrating that becomes x to the 2 upon 2, and then constant again, if you want to think of that as x to the 0 against the 2 there, if that helps you again, and follow the pattern through, that'll be plus 2x to the 1, if you like, over 1, which we just write as 2x, and then plus my constant integration c at the end there. Okay, so that's the standard approach we're using in all the questions there. All sort of standard form. 3 we've got to be careful of. We use the negative index rule there. For question 4, question 5 needs you to expand brackets by looks of it. Question 6 seems fine. Question 7, and again just separate terms there to integrate. Alright, have a go at those if you would. See how you get on with those. I'll try and follow you on the board with some of them here. Be careful with the third one there, because that's not standard form. We've got 1 over 1 divided by x squared, and that's not the standard form in the table. We're looking for a multiplied by x to the n. That would be a divided by x to the n, so that's not a standard form, so we need to be careful with that one. And what I'm going to do there is just bring the x to the top line, so I'm going to integrate x to the negative 2 with respect to x. And now that's standard form. Now that's my ax to the n again, where a is 1 and n is negative 2. That's equal to, follow the pattern through, x to the negative 1 Various ways of writing that one. Question 4 I think is fine. Question 5, just be careful, that's not a standard form as given in question 5. I'll skip question 4, have a quick look at question 5, just bouncing the brackets there. So in question 5 we're asked to integrate x plus 1, and that's multiplied by the x plus 2 here with respect to x. So we need to do the binomial expansion first of all. Remember the binomial bracket expansion, this kind of thing we did many moons ago now. Alright, so do that first of all, expand the brackets out. So don't forget we're not integrating, we're just making it into standard form. And now I've got my standard form. 3 terms, I can take each term individually. Okay, so I'll do the x squared, I can integrate, then I will integrate the positive 3x and I integrate the positive 2 constant. So take each term individually to integrate it. So question 7, we're asked to integrate half x to the negative 2 minus x plus 1 with respect to x. So they're actually all standard form here. Again, you can take each one individually. Okay, so the half x to the negative 2, we'll do that first, then we've got negative x to that next, and the positive constant. So they're all standard form. Quickly do this one. So integrating the half, that becomes a half x to the negative 1. Be careful, that's over negative 1. I'm just taking that sort of separately there. So in their final solution here, they put this negative, they sort of multiply the bottom together. So 2 times negative 1 is obviously negative 2, and they put the negative on the top line because that's the convention. So that's how they get the negative of a half x to the negative 1 minus the, again they put the half in front of the x term, so half of the x squared term plus the x plus the c. So a bit more complicated that first term there because of the fraction. Fraction always causes problems. If you put it as decimals, you'll probably find it easier to follow. Okay, I want to show you this. This isn't actually in your books. There is something in your books similar to this, but not this particular example. But I'm going to show you this very quickly. I want to talk about why we need to add this constant of integration into the expression. Why do we need to add the c? Let me try and show you this very briefly here. We're given a function, y is equal to 4x cubed plus 3x squared minus 2x plus 5, and that's polynomial function. Every term there is standard form, no other form, ax to the m. What I'm going to do first of all is I'm going to differentiate the function. So the first thing we're going to do is differentiate using standard differential tables. All right, so this goes back to what we did in previous work. Okay, so differentiate, don't forget I must put dy by dx to show I'm differentiating on the left hand side. Now I'm differentiating, so I'm following this pattern. Ax to the n becomes a multiplied by the n multiplied by the x to the n, take away 1. So in this case this will be 12x squared following that pattern plus 6x following the pattern minus 2, and don't forget constants always disappear because there's an x and naught against that one. So there's my differential. Okay, that's a differential equation. Now it could be that we're starting from that point. You can form differential equations from applying mechanical electrical principles. So that's how they derive in practice, actually a form from applying these principles. So you can actually start from that expression, and what you're trying to do is trying to get back to the y equals expression, y equals some function of x. So if I was going to now integrate this, the first thing I've got to do, following our procedure, is to multiply both sides by dx. When you integrate, you must have all the y terms on one side and all the x terms on the other. So I need to get the dx across to the right hand side of the equation. So I'm multiplying both sides by dx, so I must put the those x terms in a bracket. So 12x squared plus 6x minus 2 must be in a bracket as I multiply both sides by the dx. Now that's in the form I can integrate. I can now integrate both sides here. So I'm going to integrate the left hand side, if you like, I'm integrating 1 with respect to y, and on the right hand side I'm integrating the function with respect to x. You might say, why do you need these x's and y's and so on? Well, at higher level study you can actually get more complicated integrals where you might be integrating with respect to x, y and z. I know somebody once was looking at aerial signals and analysing those, and they can be triple integrals because they're in 3 dimensions, the aerial signals. So you have 3 integrals with respect to x, with respect to y, with respect to z. So you need to be very clear about the variables you're using, so make sure we sort of format our equations correctly. But if I integrate the left hand side, we know that becomes y. If I integrate the right hand side, now I'm looking at the integrand table here, this one here, and I'm following the pattern ax to the n through here. So following that pattern, I will get now 12x to the 3 upon 3 plus 6x to the 2 upon 2, so 1 there of course, and I'll get negative 2x. The minus the 2x. The term here is missing. We haven't got this term. So I was trying to show. Alright, so we've almost got back to the original expression, but we haven't got that constant at the end. And that's why we have to add the plus c. You must add the c. And in your notes you see this slide, which is trying to show you the same thing as on the previous page. We just start off with the expression y is equal to x squared plus 2. We differentiate it using our standard forms to get the 2x. Then they're rearranged on the next line, they're multiplying both sides by dx to get the integral of 1 dy on the left hand side, integral of 2x dx on the right hand side, and when you integrate it you end up with x squared, which of course we're missing the plus 2 again, so that's why we need to always add the c into our expression. If we are given boundary conditions, in other words we're given more information about the curve, we can actually find what this constant of integration actually is, and we'll be looking at that now. So this here is actually called the general solution, to give it a name. We can't actually use that until we know what the c is. We can't use it, but if we're given more information, we can find the c. That will produce what's called the particular solution. That means you can use it for any values of x, and we'll be looking at finding the constant c in the next slide. Just recapping the equation that's given here, the x squared plus 2 would be this curve, of course, up here, y is equal to x squared plus 2 equation, and you can clearly see that the constant there is 2. That's where it crosses the y-axis. So the constant c's relate to the intercept with the y-axis. Okay, again, this is in your notes, example 6. This is showing you the process involved in actually calculating the constant of integration here. What we're given here is the gradient of a curve. Don't forget we say gradient, that's a dy by dx, passes through a point 2, 3. And this is the kind of information we need to be given. We need to be given a coordinate. And don't forget we always read those coordinates as x, y. So that's x, y. So the x is 2 and the y is 3. And we're given the gradient equation. If you read the question carefully, the gradient equation is actually dy by dx is equal to x squared. So just read the question carefully there. It's a little bit confusing the way that question is worded. They're talking about the gradient of the curve, and they're saying it's given by, so this sort of at the end here, it's given by the x squared. So the gradient of the curve is given by x squared, and that's what we've written down here. Dy by dx, the gradient of the curve, is equal to x squared. Okay, we've got to find the equation of the curve, and that means we've got to integrate it. So the rest of the process is very similar on the left hand side here. Given dy by dx is equal to x squared, multiply both sides by the dx, and then integrate both sides. That should be an integral symbol there on the right hand side. So integrating both sides on this line, y is equal to x squared integrated with respect to x, x is 3 upon 3, plus the constant of integration. I'm just using my standard Integrand tables there. So that's the general solution we've shown here. Now if we want to find the particular solution, we need more information about the curve, and that's what we're given. We're given in the question that the curve passes through the point 2, 3, and I've just plotted the curve over here. This is the curve y equals x cubed divided by 3 plus a third, and we're given a point on the curve, so that's the point there where the curve passes through. We have to be given that information to be able to find the particular solution. I used these kind of methods years ago when I was doing beam deflections in industry, and the boundary conditions there would be a position on the beam where you know the deflection or you know the slope of the beam. That would be called a boundary condition. So we have to be given that piece of information. So 2, 3 we need to be given, and you always read them as the x and the y. So x is 2 and the y in this case is the 3 here. All we do now though is simply put those values into the equation. So into the general solution, on the left hand side I'll put y is equal to 3, and on the right hand side I'll put my x is equal to 2, and there goes my x is equal to 2 there. And I just simply work it out. Just standard equation, I call it a simple equation. I work out my final value of c, and C works out to give me a third if you go through the arithmetic there. That's purely arithmetic, rearranging the equation and solving. So I can write down my particular solution in this particular case, no pun there. So my particular solution would be y is equal to the x cubed upon 3 plus now the c, which is a third we found. I just factorised on the final line there. Okay, so that's an instance where we're integrating. We find our general solution in terms of the plus c, but we're then given further information about the curve, and it allows us to find the value of c. So we find what's called the particular solution. You can use a particular solution. You can put any value of x you like in there to get a value of y. You cannot do that with a general solution because you don't know what the constant c is. Okay, so often we need that particular solution. So that's all that example 6 is trying to show you, how to find the constant of integration. Let's have a little look at exercise 3 together if we can here. Similar kind of process involved in what we've just been doing. Okay, let's read the question. The gradient of the curve which passes through point 3, 8 is given by, so again we've got to be careful with the way it's worded. The gradient of the curve is given by x squared plus 3. That's our dy by dx is equal to x squared plus 3. So we're given a point in the question where the curve passes through, and that's the boundary condition. It's given the point here, the x comma y here. And again, always read that as x comma y. So x comma y in our bracket. We've got to determine the value of y when x is equal to 5. So they're trying to say, hey, given the differential equation, dy by dx is equal to x squared plus 3, integrate it, in other words, solve the differential equation, and then use it to find the value of y when x is equal to 5. So there's quite a bit of work in this question. So dy by dx is equal to, so this is effectively what's given in the question. Okay, reading the question, that's what they mean from the question. So we're going to have to rearrange the equation and then integrate it. So multiplying both sides by dx is our first approach here. So that will be dy is equal to the x squared plus 3 in a bracket, and we're multiplying that by dx. We're now going to integrate both sides of the equation to solve the differential. So left hand side I'm going to integrate, right hand side I'm going to integrate. So I'll get y is equal to, and these are standard forms again, we're just using the ax to the n format as always, so all in the form of ax to the n, ax to the n, our standard form over here. And that will give me the x to the 3 upon 3 plus 3x plus c. Okay, so I've integrated the expression, and that's the general solution. But in this particular case, we're given the boundary condition. So, so this was like step 1 in the process. We're going to do little steps. Again, step 2, going to find particular solution, and that's where we need the boundary condition. So given when x is equal to 3 in this case, y is equal to 8. That's from our information in the question. we can now put those values into the equation above. So y in this case will be 8, so 8 is equal to x cubed, so that will be 3 cubed divided by 3 plus 3 multiplied by 3 plus my constant. So all I'm doing there is putting the values into the equation. So x is 3 there, so that's going to go for the x term there, and then the y is equal to 8, so that's gone over there. So just putting the values into the equation. When you solve that, you should get the value of c, so therefore c is equal to negative 10. So I'm going to let you check that and see if you get the same value. You're struggling at all, hopefully you're okay with that, but that will be basically 9 plus 9 plus c. So rearranging the equation, you've got c is equal to the 8 take away the 18, and that gives you the negative 10. But hopefully you're okay with the rearrangement there. So therefore in this case our particular solution will be the y is equal to the x cubed upon 3 plus the 3x, but it's going to take away the 10 here. Okay, so that's the particular solution. That's what we found there. And the final part of the question, they want us now to find the value of y when x is equal to 5. So I'll call this step 3 in the process just to give it a handle. Find y when x is equal to 5. And that's just a question of putting the value of x into the above equation. So y is equal to 5 cubed upon 3 plus 3 multiplied by 5 and take away the 10 there. So according to my calculations I get 46.6 recurring. You just want to just check that and see if you agree with that. And all I'm doing here is putting the value, in this case, of x is equal to 5 into the equation. Wherever I see an x, I'm just putting the value of 5 into the equation. So exercise 4, we've got another differential equation to solve. This time it's expressed as dp by dt instead of dy by dx is equal to 3 minus t all squared. We've got to find p in terms of t, and we're given in the question that p is equal to 3 when t is equal to 2. That's the boundary condition. So we're going to have to find the general solution first of all, in other words find the expression for p, and then find the particular solution, find the unknown constant c. So taking the information from the question, the differential equation is given as dp by dt is equal to 3 minus t, and that's all squared. So be careful here, we've got different notation. On the left hand side, instead of dy by dx, we've got dp by dt, and on the right hand side we've got a function of t instead of a function of x. But the basic process we're going to go through is very similar. We do also need to note that on the right hand side we've got 3 minus t all squared, and don't forget that actually means 3 minus t in a bracket, and that's all multiplied by 3 minus t. So be careful of that. So if we expand the bracket on the right hand side, don't forget this is a binomial bracket, so we do our crab claw type method of expansion here. So we can write dp by dt is equal to, that will be 9 minus 6t and then plus t squared. So there's our differential equation now in terms of p and t. We next need to rearrange the equation to get all the p terms on one side and the t terms on the other. So multiplying both sides by dt, we will end up with dp is equal to 9 minus 6t plus t squared. Don't forget we need to put that in a bracket, and we're multiplying that by dt. So now we have the p terms on the left hand side and all the t terms on the right hand side. So now to find p on the left hand side, we're going to integrate the left hand side with respect to p and integrate the right hand side with respect to t. Notice that each of the forms in the bracket are effectively in the format of ax to the n in every case, or can be made into the format of ax to the n. So we're going to use our standard integrand tables to find the solution here. So integrating on the left hand side, that will become p is equal to, on the right hand side that will be 9t, notice here of course the variable is t not x, minus 6t squared divided by 2 plus t cubed divided by 3, and plus our constant of integration c. So basically step 1 has been undertaken here. We've found an equation for p, which is what the question asks us to do. So I can actually write the equation for p as 9t minus 3t squared plus t cubed divided by 3, add my constant integration again, c. And this now forms the general solution. As we are given a boundary condition in the question when p is equal to 3, t is equal to 2, we can now use this to find the particular solution. So given p is equal to 3 and t is equal to 2, we can now put these values into the general solution. So on the left hand side, p is equal to 3. On the right hand side we have 9 multiplied by t, so 9 multiplied by 2 minus 3 multiplied by t squared, 3 multiplied by 2 squared, and then we add the t cubed upon 3, so that's 2 cubed divided by 3 plus the constant integration. Evaluating, we have 3 is equal to 18 minus 12 plus 8 divided by 3 plus c. Solving that equation, we will find that c is equal to negative 5.6 recurring, or negative 5 2/3. So again, just to recap, all we've done there is put the value of p into the equation. So p is 3 in this case, so that's p on the left hand side of our equation over here. And the value of t in this case is 2, so we put 2 wherever we see a t in our general solution. So t, and t, we put the value of 2 in, and just evaluate to find the constant c. So our final solution will be p is equal to 9t minus 3t squared plus t cubed divided by 3, and now minus the constant integration, which is 5.6 recurring. And that's the particular solution. So what we've looked at up to now is actually called indefinite integrals, and with an indefinite integral you always end up with a plus c at the end of your expression, always. What we're going to look at now is something called definite integrals. Slightly different. These are the ones you can actually perform on your calculator. Some of you may have a calculator button. You might see a button like this. You've probably got a blob there and a blob there and perhaps a blob there. And it probably says dx, something like that. I'm not quite sure exactly what the format is, but some calculators have this kind of button. It does numerical integration. And that's the kind of thing we're actually going to look at now. We're going to look at solving definite integrals. So these will not end up with expressions. These will end up with pure numerical values. Because the difference now is that we're going to have what's called limits, top and bottom of our integral. So an indefinite integral would be, as we've seen in the previous questions, something like integral of 3x squared with respect to x. That's a standard indefinite integral, and that will end up with a plus c in the solution. What you're going to see now are the definite integrals, and you will end up with, as I say, numerical answer as the final solution. So a definite integral example is this one here on the right hand side here. When we're integrating x to the n with respect to x, so that bit's the same as we've seen in the previous work, but what is different now are the limits we have, top and bottom. We have a and a b. Those are called the limits of integration. The a is called the lower limit, and the b is called the upper limit of integration. And that's the only thing that's different about the integrals you'll see. They will have those limits on. But what it does mean now is it will be able to put the limits into the integral and will actually solve for a pure numerical value. Okay, so nothing changes as far as the integration process is concerned. We'll still be using this standard form, integral of x to the n respect to x. We're still getting our standard integral, but we won't, you'll see in a moment, need the plus c, and I'll show you why you don't need the plus c anymore when you're dealing with definite integrals. In this example here, we've got to integrate the x squared with respect to x, so this part of the expression, exactly the same as we've done before. Integrate y equals the integral of x squared with respect to x, but this time between the limits of 3 and 2. And what this example is trying to show you is that you do not need the c anymore. Let me try and take you through this very quickly here. So on the left hand side we've got the problem here where y is equal to the integral of x squared with respect to x between limits of 2 and 3. If we integrate x squared, we know we get x to the 3 upon 3, or a third of x cubed. That's standard form, that's our integral. And we know we have to add the plus c, which I've highlighted in yellow there. So in that square bracket there, we've got the third of x cubed. That's integrated x squared with respect to x. But we've added the constant of integration. You notice a slightly different format now. I've put that in a square bracket, and I've put these limits, the 2 and 3, which were on the integral sign to begin with, I put them at the back of the brackets, and I strongly encourage you to adopt the same formatting as I'm using. This is not my formatting, this is the standard formatting we use in these solutions, and I can tell you from experience, as you get to more advanced problems, this formatting is very, very useful. So try and get familiar with this formatting now and use it as I've shown. So square brackets, inside we've got the integral with my constant of integration there, and the limits are on the back of the bracket. Okay, all I've done on the next line is written it is x cubed divided by 3, because most students prefer that format. Okay, so x cubed over 3. Now what we do now is what's called impose the limits. We're going to impose the upper and lower limits into the problems. So the 3 is classified as the upper limit, okay, and all I do is put that value into the equation we've just generated. So there's the x cubed, so that will be the upper limit of 3. So x cubed divided by 3, that will be 3 cubed divided by 3 plus my c. So that's the upper limit going into the term. That's called the upper limit there. And then we put the lower limit into the equation, and the lower limit in this particular case is 2, so there's the lower limit, and we simply put that in for the x there, and this is called then the lower limit of the equation. I'll just put the 3 into the first bracket and I'll evaluate that. I put the 2 into the second bracket, and you always subtract. There's always a subtraction between the two. That's always, you always subtract the lower limit from the upper limit, always. That doesn't change, okay, in the process we're going to do. So if you now go to the numbers, then 3 cubed divided by 3 would give me 9, there's a 9 there, and then 2 cubed divided by 3 would give me 8 divided by 3, and that's what's shown there. What you notice though is the plus c's are in both brackets. I've got a plus c in the first bracket and a plus c in the second bracket, but as we're taking the second bracket from the first bracket, when I expand that second bracket, the negative then, don't forget, affects both of the terms there, so that negative makes this term a negative, but it also makes the constant c a negative, and that's what you're seeing here, negative and negative. So that positive c is cancelling with the negative c. So I end up with a pure numerical value of 9 take away the 2 and 2/3, give me 6 and 1/3. Don't worry if you don't understand the full details of that at the moment. What I'm trying to show you there is when you've got limits on your integrals, you've got these numbers on the top of the integrals here, when you've got limits you never need to add the c in, because it always cancels out. You can add it in if you want to, but it just complicates your calculation and it will always disappear. So whenever we're dealing with a definite integral, and that's where we have limits top and bottom of our equation, we never need to add the plus c because it will always disappear, and that's all that example 5 is trying to show. Okay, what I want to do is go through some exercises using the definite integral. The integration process is not changing. What we did in the first part of the lecture, we're doing exactly the same thing now. It's just that we'll be calculating a value for the final integral here. So let's start with exercise 5. So we've got to solve the integral of the x squared with respect to x between the limits of 1 and 2. 1 is the lower limit and 2 is the upper limit. Standard form integrating from my standard tables, I will get now x to the 3 upon 3. That's just following the ax to the n pattern through as we find the integral. But don't forget, we're going to put that in a nice square bracket now, and we're going to put the limits of 2 and 1 at the rear of the bracket. Okay, that's integration done. So x squared integrated with respect to x is x is 3 upon 3, and it's between the limits of the 1 and 2. So putting my limits in now, get my square bracket here, so putting the upper limit in, that will be 2 cubed divided by 3, and we always take away the lower limit, so in this case that will be 1, I'll put the cube there, divided by 3. And that's just an evaluation exercise. We're just going to evaluate these. So according to me, the answer there is 2 1/3, or 2.3 recur, whichever you prefer to use. And again, it's just putting the upper and lower limits in the equation. In this case, the upper limit is 2, so 2 went into the equation for the value of x, and then we put the lower limit in the equation. So 1 goes into the equation for the value of x. Something else I just mentioned here in passing, but it doesn't affect what we're doing effectively, but don't forget what I said to you right at the beginning of the calculus lectures we were having. When you're integrating, you actually find areas under curves. So just for interest, what we're doing here, if you take example 2, we're given the equation, or given the problem of integrating 2x plus 3 with respect to x between the limits of 2 and 3. Here's my diagram, okay, of x and y. Now if I was to plot the equation 2x plus 3, that would be a linear line, so of the form y equals mx plus c there, a linear line, gradient of 2, and it would cross the intercept. The intercept with the y-axis would be at 3. So if I was just to sketch the line, all it would look like is something like this, okay, where that in this particular case would be 3, and the gradient of the line would be 2. Now what the integration process is actually doing is saying, what is the area between the limits of 3 and 2? So basically what this integral is trying to get us to calculate is between these values here of 2 and 3 on our x-axis, it wants us to find the area under the curve. Okay, so actually what we're doing is finding this area on that particular curve, knowing that the equation of the line in this case, the y is equal to 2x plus 3, and that's what integration does. It finds the area under the curve. So although it doesn't say it in the question, that's effectively what we're doing. We've got a linear line and we're finding the area under the curve between the values of x, 2 and 3. Okay, doesn't affect what we're going to do, but a little bit of background for you there. So I could, if I want to, I could write this area equals to, because that's actually what it's calculating. And of course the area relates to the context. If it was going to be I don't know, a force distance diagram, then the area would be work done, for example. If it was a velocity time diagram, then the area would be distance travelled or displacement. So it relates to contexts, but that's kind of what we're doing with these equations. So I could write, if I want to, area equals to the integral of 2x plus 3 with respect to x between the limits of the 2 and the 3. So we just need to integrate that. It's all nice standard form. So that becomes 2x to the 2 over 2 plus 3x. Don't forget we put that in a nice square bracket, and we put the limits at the back of the bracket. Let's keep this kind of format here. Bit of cancelling there. I'll get rid of the 2's there. So 2 divided by 2 will be 1. So let's rewrite that. I like to get my expressions as simple as I can make them. Makes the calculation a bit easier and a bit clearer to follow. So that's just a bit of simplification there. And then just put the upper and lower limits into the equation. Let's put the upper limit in first of all. So again, be nice and structured. What's the way I'm doing this? I'm going to put the first limit in a bracket. That will be 3 squared plus 3 multiplied by 3. That's in my bracket. That's the upper limit, and I'm going to subtract from that my lower limit. So subtract lower limit, that will be 2. So 2 squared plus 3 multiplied by 2 in my bracket there. Keep it nice and structured as best I can here. So my upper limit of 3 is going in here, and here my lower limit of 2 goes in here and here. Okay, and then the rest of it is evaluation on your calculator, whatever you're using. So I get my 8 from, so 8 units squared, whatever, in this particular case. This is a quadratic. I'll let you have a go at this one, because very similar process here. We're given a function x squared plus 3, symmetrical about the y-axis, but going through the y is equal to 3, pass through the point 3 on my little diagram here. This is y, this is x, and it wants us to find the area under the curve this time, effectively, because we're asked to integrate it between 0 and 2. So in this particular case, we're finding the area. I don't know what the scale would be here, but if I call that point 2, this would be point 0. We're finding the area under the curve shown there. So that's for the function y is equal to x squared plus 3. Okay, so that's what we're doing. We're finding the area under the curve using the integration process. You've probably finished that question now by the time I've done all that. So the area is equal to integral of x squared plus 3 with respect to x, and limits of 0 and 2. That becomes x to the 3 upon 3 plus 3x. Again, make sure that's in a nice square bracket, and then impose the limits. So I will get the 2 cubed upon 3 plus 3 multiplied by 2, and I will subtract from that lower limit. Now that's 0 in this case, so I can see everything's going to go to 0. You need to be careful with the 0 limit. It doesn't always go to 0. If you're using a cos function, for example, that wouldn't go to 0. So that will give me where to get the 8 2/3 from, or in a decimal, 8.67 to 2 decimal places. Sometimes. Okay, determine the area. Let's have a quick go at this one then. So the area is equal to the integral of 2x squared minus 10x plus 8, integrating with respect to x between the limits of 1 and 4. All the standard forms here, so let's go straight for the integration. So I end up within the first bracket, the first bracket of minus 5.3 recurring, and then I'm taken away 3.66, and that's how I get the final answer of minus 9 in this case. You've gone through everything you need to know now about integrating polynomials at ax to the n. You have lots of examples, and that's an actual example. They might say in the question, find the area under the curve, some kind of question like that. So, but it's all based around that kind of problem you're doing there. What I want to go on to is to look at the standard integral table, but other functions. So we know about the ax to the n. We've been looking at that one in all the sessions. The next one we've got to be able to be aware of is the sine ax. Okay, now when you integrate that, don't forget we're integrating here, when you integrate that, that becomes negative cos ax upon a plus my c if you have no limits. If you look at the cos function, the cos ax integrates to sine ax upon a plus the c. Don't forget the a's are just numbers here, so that could be cos 3x integrates sine 3x upon 3. That's what the a relates to as a constant. And the final one then we've got to be aware of is the exponential. The e to the ax integrates to e to the ax divided by a. I'll just show you that on a slightly different expression here. Just make it clear to you. So what they've given us there is 1 upon a multiplied by e to the ax. But you could also write that as e to the ax divided by a. The same thing. Multiplying by the 1 upon a is the same as dividing by the a. Okay, just different formats, that's okay. Now I actually think these are easier to deal with than the polynomials because there's very little change in the format of these equations. The sine ax and the cos ax, hardly differ. So when you've done a few of them, they really are very, very similar. It's just the e to the ax can sometimes be slightly problematic because it can have a negative a. So it's slightly problematic in that respect. But generally speaking, these do not really vary that much. So I'll just take you through the example very quickly here. So looking at the first one, up here we're asked to integrate 12 multiplied by cos 3x with respect to x. So the part of the equation we're interested in there will be the cos 3x. So that's the cos ax bit. That's cos ax, okay, that bit there. So looking at the cos ax function here in the tables, cos ax or cos 3x sine ax upon a. So in this case that would be sine 3x upon 3. So that's the actual integration we're doing. So integrating cos ax, cos 3x, that becomes sine 3x upon 3 when we integrate it. And the 12 in the front is just factoring up the expression. It's 12 multiplied by sine 3x upon 3. Notice I've had the constant c here because there's no limits in the integral. There was no limits, no numbers on my integral sign, so I had the plus c again. And all I've done on the next line is just divided 12 by 3 to get the 4 sine 3x. Next one I'm looking at is the exponential function below. I'm given 5 multiplied by e to the power of 10t in this case. I've got to integrate with respect to t, but again that's just like an x. So if you look at the standard forms in the table, e to the ax integrates to e to the ax divided by a. That's what that's showing you there, e to the x divided by a. So in this case that would be e to the 10t, e to the ax, and I divide it by the a, I divide it by the 10. So again we had standard form. This form was e to the ax. 5 just multiplies up the exponential function. On the next line I just divided by the 5 by the 10 to get the 0.5. That's just a division sum there. So 0.5 e to the 10t plus c. And of course you can have, it shows in example 3, you can have two functions together. I've got a cos function and an exponential function there, but I just apply the integration process to the terms separately as I did in the previous work. So just separate terms. So integrating the 8 cos 4x, that will integrate to 8 sine 4x divided by 4, or 2 sine 4x if I cancel down. And if I integrate the negative 3 e to the 4x, that integrates to the negative 3 e to the 4x upon 4, and again I just cancel down the 3 divided by 4 there. Okay, so that's the way we use the tables. We just use those standard forms there, help us integrate the functions. And the last one there we've got, it's got 3 functions now. We've got a sine, a cos, and an exponential, and they're all standard form here. They're all of the table format. That's sine ax in the table, cos ax in the table, and of course e to the ax in the table. They're all standard forms, and we can just take each of the terms individually and we can integrate them. Okay, and that's what it is on the right hand side. So here's some questions to I'm going to leave you with, really, to have a play with these questions. They're all forms of sine, cos, exponential, that kind of thing, to be aware of. The only ones that are slightly tricky, I would suggest, are the latter ones. The first ones are all in standard form. We could integrate this one. This would be the sine ax, and this would be cos ax. They've changed the variable on us, but don't let that bother you. This is just a 2 outside the integral, so it's still sine ax, and so that negative 4 could be outside the integral, so we've got cos ax. You can see they're all standard forms here. This is e to the ax. This is that 2 could be outside the integral, that's just e to the ax here. Now this is the only one that's slightly tricky here. Be careful with this one. That's 6 over e to the 1t. Now in that particular case what I would do is to bring the et to the top line, so I'd actually start from 6 e to the negative t with respect to t. So I'd bring the e to the top line to integrate that. Now I'm back to my standard form then of e to the ax, where the a is negative 1 in that case. So just be careful of that's a negative 1. Okay, and the same with this one down here. Be careful of that term there. That would have to be brought to the top line, so 4e to the negative 2x before you begin. But the rest of them are in standard form. What I might just do, just to finish off with you last few minutes, just have a go at exercise 7, perhaps the first example in exercise 7 here. So we're going to integrate here, brackets is 6 sine 2x plus cos 4x minus 2 e to the 4x. We're integrating with respect to x, and I said they're all standard forms here. If you look in your tables now, sine ax, cos ax, and e to the ax, all standard form. So on the next line I can just integrate them, so that will be, so integrating the sine goes back to the negative cos in your table, 6 cos 2x upon 2, and that'll be a negative when we integrate the sine function. Next one, plus, integrating that will be sine 4x over 4, and integrating that will be negative 2 e to the 4x upon 4 plus my c. And I can simplify that. So negative 6 divided by 2, so negative 3 cos 2x plus my, you can write as a quarter if you want to, just write it differently, quarter of the sine 4x, just to be different there, and then that will be negative a half e to the 4x plus my constant. And they're all very similar. All that's happened in the other question, they've changed variables. For example, we've got variable of t in the second question, we've got variable of theta in the fourth question, variable beta in the fifth question. I find that in the exams they very seldom would change the variables. It's normally y and x in most of the expressions, but just to show you the practice of how these can be stated to you. And that's basically it. If you can do those questions on the slide there, then basically you're absolutely fine with what you need to do for this end of the topic, really.